with two things that aren't quite mathematical. So the first thing is I want to recognize that I live and work on the ancient homeland and traditional territory of the Lenape people, and to honor the Lenape people and other indigenous caretakers of this land. I also wanted to mention that today is the Stop Asian Hate Virtual Action Day. So this was initiated in part by Grace Mung, one of the representatives from Queens. So the mass shooting in Atlanta last Tuesday is one of the latest examples of violence against Asian Americans and against Asian American women in particular. And so I think we should all condemn these acts of racism, work together to stop Asian hate, and stop these racist and sexist attacks. And if you want to know more about what activities are happening today, I think if you just Google Virtual Action Day, Stop Asian Hate, you'll be able to find some. But with that, let me get started with the mathematics. So today I want to talk about Boutot's theorem for quasi-excellent Q-algebras. And for a while, I'm not going to talk about any of the things in that title, but I want to introduce maybe first the main question for the day. So the main question is, if I have a ring S, so in this talk, all rings are commutative and unital, I guess. And suppose I have a group action on it given by a group G, and it's acting by ring automorphisms. So the question I want to ask for today is, what properties of S are inherited by the ring of invariance, which I'm going to denote by S to the G. And so this is kind of a really general question. And so for most of this talk, I'm actually going to try to motivate it with some history. In the first part, I'll talk about the historical motivation from the 19th century, which is Hilbert's 14th problem. Then I'll talk more about the more modern perspective, and in particular, the theorems of Hoxer, Roberts, and Boutot. And the last thing I'll do is talk about the title of the talk, which is Boutot's theorem in this more general context. Okay. So with that, let me get started. And if you have any questions, feel free to let me know. I'm going to keep the chat window open on my computer, so I'll be able to see anything you type as well. So let me get started with the motivation from Hilbert's 14th problem. So Hilbert's 14th problem was one of Hilbert's problems that he introduced in the ICM in 1900. So I think they were published, so it's 1900. The English version is in 1902. So if you don't read German, but you read English, that would be a good place to look. And Hilbert asked the following. So he said, okay, let K be a field. Now let's consider an algebraic subgroup of the general linear group in n variables over K. And so by that, I mean it's Zariski closed. It's defined by, algebraic subgroup. It's defined by some polynomial equations. So to tie this back into my main question, let's let S be the polynomial ring in n variables. And then I can consider the action of this group G considered as a subgroup of GLN. So if you consider GLN, it acts by some linear transformations of the variables. And so you can transfer the action of G onto this polynomial ring. So Hilbert's question is, in this case, is the invariant subring S to the G of finite type over K? So does it have a finite number of generators as an algebra over K? Are there questions about Hilbert's question? Okay, so I can tell you a lot about it. Let's start with an example of where we know the answer, which I think is fairly classical. So Again, let me write down what the ring is. It's a polynomial ring in n variables. And we're going to act on it by the symmetric group. So I'm no good at drawing the fractor S. So here the S is different from the one on the left. This is the symmetric group on n letters. Okay. And so you can ask, what is the invariant subring in this case? And so here you get the ring that's generated by the elementary symmetric functions in these variables. Right. And one thing you learn about in abstract algebra is that if you consider these elementary symmetric functions, they're all algebraically independent. So in this case, you actually get something that's isomorphic to the original polynomial ring, except with different variables. So in this case, you can actually see that you have something that is of finite type over the field. Okay, and this is the first time I scrolled past, so I'm going to use 2 columns. And each time I'll scroll on one side so you can follow the previous slide, so to speak. So if you want me to scroll back, I can also do that as well, but hopefully this gives you some continuity between slides. Okay, so let's do a second example. This time I'm going to consider a bunch of variables, and I'm going to consider them as entries of a matrix. So X here represents an R by T matrix. And Y here represents a T by S matrix of indeterminates. Okay. And so this is also a polynomial ring, right? It has like R times T plus T times S variables. And we're going to consider a GL action. Let me make sure I get the right number of variables. It should be T, I think. Where if I have all these variables, I'm going to map them as if I'm multiplying on the right by A inverse and on the left by A on these 2 matrices X and Y. So this defines an action of the GLT of K on this polynomial ring. And you can also ask what the invariant subring is in this case. And it ends up being the subring generated by the entries of the matrix X times Y. So it has a bunch of things that look like xi times yj and some sums over those. I won't write down explicitly what it is. So just by the fact that there are finally many entries of this matrix, it's still a finite type over a field, over K even. In this case, you can actually write down what its generators are. So if you consider just a generic matrix, that's R by S of indeterminates, then it surjects onto this ring, and the kernel is given by the T plus 1 minors of this matrix U. Or T by T minors, I think, actually. Okay, hopefully I got the numbering right. But basically, it's a determinantal ring, right? So it's something very nice, and it's a finite type over K. Okay, are there any questions about these examples? I'm going to tell you what we know in general very soon. Okay, so let me tell you what we know about Hilbert's 14th problem in general. And so I guess the short version is, yes, this is true in a lot of cases. And the cases we know are for reductive groups. So I'm not going to define what these are, but I'll tell you out loud some important examples. For example, Hilbert himself back in 1890 proved the case when G is SLN over the complex numbers. So I think he proved it for specific actions, but the same proof works for a lot of other things. Emmy Noether in 1916 and later in 1926 proved the case when G is a finite group. And I wrote it 2 dates here because 1916's proof is only an equal characteristic 0, and 1926 was an arbitrary characteristic.
But don't you have to have that the characteristic doesn't divide the cardinality of the group?
Oh, yeah. So I thought this too, but the 1926 proof doesn't need that.
Yeah, no.
Oh, no, it doesn't. Oh, really?
Yeah. So it's very interesting, actually. So I'm going to show you that in
the bound of the group order depends on the characteristic, but not the fact that it's finitely generated.
Yeah, thank you. And they'll set me up better later too. I'm going to show you the proof when G is like the order is invertible. Okay. So Weil in 1936 proved the case of like classical groups. So like, GLN, SON, all those kinds of things. And was a lot of action between then and the last result I'll mention, which is by Habush in 1975, which is all reductive groups and arbitrary characteristic. So this was a long-standing open conjecture. Well, I guess, Mumford conjectured that this should be true, and Habush proved that this is indeed the case. Okay. And the other end of the spectrum is that, it's not true in general. There are definitely groups where this finite generation does not work. And these examples are due to Nagata in 1958. And there have been later examples too, but Nagata is the first one that came up with them. So this kind of gives us a pretty complete picture of what's true about Hilbert's 14th problem. Do people have questions about these different cases? As I said, I'm going to show you a proof of one part of them, which is Noether's. And one reason why is because, one, it's relevant to the rest of the talk, and two, it was Noether's birthday on the 23rd this week. So I think it's a good timing for mentioning her results. Okay. And so I'm not going to prove the most general part of Noether's theorem. In particular, I'm going to assume that the order of the group is invertible. But here's the version that I'm going to prove. Let's let S be a Noetherian domain. And let's consider the action of a finite group where the order of the group is invertible in S. Then the claim is S, the invariant subring, is Noetherian. So Hilbert's 14th problem is about finite typeness. I'm not going to prove the finite typeness part. I'm just going to prove it's Noetherian because I think it's instructive for the rest of the talk. And just to make it coherent with the rest of the notation I'll use in this talk, I'm going to denote S to the G by R pretty often. Okay. So step one, how do you prove this? Well, I'm going to prove it by showing first that in this case, this map from R to S is pure. And I'm going to be using this notion a lot in this talk. So this is partly just to get us used to thinking about what this notion means. And so the definition is that for every R module M, we assert that if you tensor up the map from R to S by M, they should remain injective. Right? So we're looking at the inclusion of the invariant subring inside of S, and the claim is that this is injective after you tensor by an arbitrary R module M. And so how do we prove this? Well, there exists a splitting as a map of R modules of this inclusion map. Let me write it down. So S to the G maps to S and maps to S to the G, where the map is given by S mapping to 1 over the order of the group times the orbit of S under the G action. And so this kind of operator is called a Reynolds operator. Let me write it down over here. And what does it mean to be a splitting? I'm just saying that the composition from R to R here, this is the identity. So this kind of tells you why invertibility of the order of the group is very important. And why does this tell you that it's actually pure? This map here, when you tensor up by M, also has a splitting. So that concludes step 1. We know this map is pure. Any questions about step 1?
Could I just ask, this is just not really about the step, but that conclusion, obviously the proof depends on the non-modularity hypothesis that the group order is invertible.
That's right, yeah.
But that means, does the conclusion also depend on that? Like, does purity fail in the general case?
I think purity does fail in the general case. Like if you have the order of the group dividing, or the characteristic dividing order of the group, but I don't really remember an example, so
Okay, thank you.
that's what I'll tell you. Yeah, thank you. Okay, and what is step 2? The step 2 is the more general statement, which is that if you have a pure ring map, where S is Noetherian, then R is Noetherian. So I'm going to use this fact later, which is why I'm proving something more general than the theorem statement. And so what is the proof here? Well, first, let me make the following observation. If you apply the definition of purity to a cyclic module, R mod I, where I is an ideal, we see that R mod I injects into S mod IS, after identifying the tensor product with S mod IS for all ideals I and R. And another way to write this is that if you extend the ideal I to S and then contract it back, you end up with I. Okay, and so why is this important? So if you take an ascending chain in my original ring R, you can extend this to S. And since S is Noetherian, I know that this chain must stabilize at some point. Okay, so now I can contract back to R. And since the map is pure, I end up with the original chain I wanted to show stabilizes. And it in fact stabilizes at the same place N. So that tells you that R is Noetherian. Okay, are there any questions about these proofs? Okay, I'm going to use this fact again. So when they say that a pure subring of a Noetherian ring is Noetherian, this is what I mean. So before I move on, let me give you a few remarks. So first of all, Noether's proof is very different from this. In particular, since the 1926 proof requires, it doesn't need the invertibility hypothesis, naturally you would expect that you need to do a different kind of proof. The second thing I want to note is that this proof can be adapted to work for all linear reductive groups. And so I'll just say this out loud, but we had this Reynolds operator where we averaged over the group orbit. You can imagine you take an integral against the Haar measure or something like that, at least in the case of Lie groups, to get you a similar operator in other settings. And the last thing I'll note is that Hashimoto in 2005 proved that finite type also descends under pure maps. So I showed that Noetherianity does this. The proof of finite typeness is more complicated, but it's still true. So
is this result, what you actually use is not really even pureness, but you use cyclic, what they call cyclically pure, right?
That's correct, yeah.
Is this result of Hashimoto also true for cyclically pure, or that really needs purity? You know?
So I haven't read the proof carefully enough to know if cyclic purity is enough, but at least Hashimoto states it for purity.
Oh, okay. Okay, yeah, I don't know that paper, so that's why I'm asking. Okay, thank you.
Yeah. It's actually pretty interesting. So he uses like the Raynaud-Gruson flattening theorem. So it's like much
really?
more, yeah.
Oh, okay, I have to look into it then. Okay.
Yeah. Okay, so let me move on to the theorems of Hochster-Roberts and Boutot, which is going to be the focus of the rest of my talk today. And so we just talked about the finite type condition and the Noetherian condition under, pure subrings. So the question that I want to ask now is, what about singularities? So like other properties of rings. So for example, let me just start with this proposition that I learned from the paper of Hochster and Roberts. I don't know if it's older though, so what do Hochster and Roberts prove? So one thing that they prove in this paper, which is not their main theorem, which is that if you have a pure map of rings and S is a normal domain, then R is also a normal domain. And this is something else that I'm going to use later, so I might as well prove it for you. So let's let R be a subring of S that's pure, and let's consider the corresponding inclusion of fraction fields. And if I want to show that R is normal, that means it's integrally closed in frac of R. So B over A, an integral element over R, we need to show is actually in R. Okay. So how do I go about doing this? Well, we know that S is normal. So B over A is an S, right? Because the same integral dependence equation works over S. Just by rearranging this inclusion, that means that B is contained in the principal ideal generated by A and S. I can contract this back to R because B is an element in R. And by purity, I know this is still the principal ideal generated by A and R. And so this shows that B is divisible by A, and in fact, B over A is in R. So again, I'm only using cyclic purity here, I guess, but if you have a pure subring of an integrally closed domain, this shows that, that pure subring is also integrally closed. Okay, are there questions about that proof? Okay, so this tells you what happens for normality. You can ask what happens for other conditions. And I use the word singularity here. So you might ask, well, what happens for regularity? And the answer is no. So let me give you one example where this happens, and similar examples can be written down for other groups. So I'm going to consider the Z mod 2Z action on the polynomial ring in 2 variables. Let me put the characteristic assumption here that it's not 2, because Z mod 2 and characteristic 2 probably don't work well together. And I'm going to do this map where I just attach a negative sign to both of the variables. So that should be a 1. This invariant subring is now going to be the Veronese of degree 2 inside of the original ring. Right? So like, these are obviously in the invariant ring because, if both of the variables get switched signs, then their product definitely will not change sign at all. And this is not a regular ring. So one way to see this is that dimension of the cotangent space, so m mod m squared, is 3-dimensional. It's generated by those 3 monomials. But this is a Cole-Macaulay ring. So in this case, x1 squared and x2 squared give you a homogeneous system of parameters that's a regular sequence in the maximum ideal. And so you could say, okay, maybe this happens in general. Maybe a pure subring of a regular ring is always Cole-Macaulay, and that is the theorem that I'm going to state now. So I'm going to tell you who it's due to later because it's due to many people. So if you have a pure inclusion of rings and S is regular, then R is Cole-Macaulay. And even better, it's pseudo-rational. So I'll tell you what pseudo-rational means later in some cases. But for now, just think of this as a stronger version of Cole-Macaulay. Or maybe not a stronger version, but it's a stronger condition than Cole-Macaulay. Okay. And so let me tell you some cases of where this is known. Is the statement okay? It makes sense? Okay, and hopefully the example tells you why, if you're optimistic, maybe you think it could be true. So this is one of those theorems that has different proofs and different characteristics. Oh, the line got cut off. So in characteristic P, the Cole-Macaulayness was proved by Hochster and Roberts in 1974. So they actually proved this along with the characteristic zero statement that rings of invariance are Cole-Macaulay. But to prove that all subrings of regular rings are Cole-Macaulay and equal characteristic zero, so I'm going to write that as R contains the rational numbers. This happened later in a paper of Hochster and Hünicke in 1995. Okay. So that tells you two cases where this is known. The pseudo-rationality, the first result in this direction is due to Boutot in 1987. So he actually needs the assumption that R and S are essentially a finite type over a field, which means you're a localization of a finite type algebra over a field. And then the general case is due to Hans in 2008. I'll tell you more about these different proofs in a bit. In characteristic P, the pseudo-rationality is due to Smith in 1997. And the last thing I'll mention is that in mixed characteristic, this is a fairly new result that relies on this new perfectoid stuff that's been going on. And it's due to Ray Heitman and Lin-Chuan Ma in 2018. So you can ask him next week about the theorem if you have more questions. Are there questions about these results?
I assume you're going to give us a definition of pseudo-rational soon.
Yeah, so maybe not soon, but in a couple of minutes, yes, definitely.
So here in the theorem is the regularity necessary. Can you weak the condition for S? Let's say just we ask S to be Cole-Macaulay.
Let's see. So it's not true that a direct sum end of a Cole-Macaulay ring is Cole-Macaulay, if that's what you're asking. I don't have an example off the top of my head. So maybe one thing I'll mention is that in the 70s, Mel has like a couple survey articles on like invariant theory and his paper with Roberts as well, where he talks about how like Cole-Macaulay condition is not strong enough to guarantee that it passes to a pure subring, and gives a lot of other examples. So, these examples I really just took from him. But yeah, okay. Are there other questions?
Sorry, I don't know whether this, these rings are local or you don't even need that?
You don't need local.
Okay.
Yeah, so it's kind of complicated, but you can localize R, and then there's some localization of S that passes the purity condition, but regularity is stable under that, and so is Cole-Macaulayness, so that's fine.
Yeah, okay. Yeah.
Okay. So let me tell you some comments about these proofs, because I think it's interesting how different these different proofs ended up being. So Hochster, Roberts, and Smith they're in the characteristic P column, so you might expect that they use Frobenius techniques. Boutot uses vanishing theorems. So this will be what I talk about in the last section of my talks. I guess Hans adapted Karen Smith's proof. To characteristic 0 using ultra products. Is that a fair description of your proof?
Yeah, but that's exactly how I would state it. Yeah, thank you.
Okay, good. Just checking. And then Hoxter, Hunicke, and Heitman-Ma use one of the homological conjectures. So it's the weak functoriality of big Cohen-Macaulay algebras. So I'm not going to talk about this today. So functoriality. So I won't mention what this means, but hopefully this gives you some context if you are familiar with these sorts of homological conjectures. I mean, more specifically, I guess I'll mention that Heitman and Ma passed through this vanishing of maps of Tor conjecture. But that's, yeah, definitely not what I'm talking about today.
I think that might be, I forget now exactly, but the original proof from Hoxter, Hunicke and characteristic 0 might actually be a lifting technique from the characteristic tight closure proof that they have in characteristic P.
Let's see.
I think there are two. You can also prove it that way, I think, and that doesn't need. They have also a technique of lifting characteristic 0, tight closure to characteristic 0 product, but not the Boutot proof. That they cannot do. But the Hoxter, but the property 1 is just Cohen-Macaulay. I think that just goes through. Or perhaps I might be wrong.
Okay, well, maybe I'll look at their paper more carefully, but at least one of the proofs they give uses big Cohen-Macaulay.
No, perhaps not this paper, but they have a paper on tight closure characteristic 0 where they, but it's a long work, and they might have had it there. But so I think what you write down with as 95, this might be their first proof, might be correct now. Now I think about it. Yeah.
I see. Well, I guess, nowadays you can also use your like ultra tight closure or non-standard tight closure to get the same proof. Yeah. Okay, so let me state my main theorem, which is a more general version of Boutot's theorem. So let's let R be a Q algebra and suppose it's a pure subring of S, where R and S are satisfy this technical condition called quasi-excellent. I'm going to also define this later. And what I prove is that if S is pseudo-rational, then R is pseudo-rational. And again, this is a version of Boutot's theorem. So I didn't say this before, but Boutot actually proved a stronger version of the theorem that I wrote down before. Which is that you can weaken the regularity assumption on S to pseudo-rational. And he proved the case when R and S are essentially a finite type over a field of characteristic 0.
Yeah, and then it's just rationality. You don't have to say pseudo-rational anymore, right?
Oh yeah, that's right. But I don't want to define two different words in the talk. So I'm going to stick to the word pseudo-rational.
Okay.
And the other thing I'll mention is that the main theorem answers first a conjecture of Boutot in that 1987 paper, and also a question of Hans in the quasi-excellent case. And this quasi-excellence is kind of annoying, but it is very important for my proof. So, and so let's see. So my notes actually define quasi-excellent first and then pseudo-rational later. I hope that's okay because we do need the notion of quasi-excellence for at least my definition of pseudo-rational to make sense.
So what's the word EFT over a few? What's
Oh,
the,
sorry. It's essentially a finite type. So I said this earlier, but it's a localization of a finite type algebra.
okay.
Yeah. So I think in commutative algebra, we really like working with local rings, right? And so if you take a finite type algebra and localize it, suddenly it's not finite type anymore. But we want to have those rings included. So that's why it's called essentially a finite type. Okay. And so let me tell you one definition of quasi-excellent that works in my case. So the fact that this is a good definition is due to Temkin in 2008. So if you have a Q algebra R, it's quasi-excellent if it's Noetherian. And the second condition is that for every domain that's module finite over R, so finally generated as a module over R, there exists what's called a resolution of singularities of that ring. So I'm going to denote it by W. And let me tell you what that means in a more commutative algebraic way. So this means that there exists some ideal inside of T such that when you take the proj of the Riesz algebra generated by this ideal I over T, this is regular. And this is what ends up being this space W. And so if we're not used to, well, I use the word quasi-excellent a lot in my papers, but I think it's better to just tell you that most rings you would care about are in fact quasi-excellent. For example, all complete local rings are quasi-excellent. I'm going to abbreviate quasi-excellent by QE a lot, I think. And also this class is stable under localizations and also under finite type ring maps. Okay. So this is what quasi-excellent means, and I'm going to use these resolutions pretty often. Are there any questions about this definition?
Well, the first term that I think of when you say quasi-excellent is excellent rings. So how does it relate? Are all excellent rings quasi-excellent?
Yes, that's right.
This is so funny. I was gonna exactly having the same thought. Okay, so it's a double question then.
Okay.
Yeah, so excellent implies quasi-excellent. So the extra condition is this universally catenary condition. So I don't really want to define this right now, but basically if you have two prime ideals in a ring, you can look at different chains of prime ideals between those prime ideals, and they could be of different lengths. But universally catenary means that first of all, the maximal chains are all the same length, and also that this is stable under finite type ring maps. And so so that's a stronger condition than quasi-excellent. So excellent equals quasi-excellent plus universally catenary.
Thank you.
Okay.
Yeah.
So then the next question is, are there non-quasi-excellent rings? Because, okay, it's resolution of singularities, characteristic 0. So it's strange that all of a sudden there's a ring that we cannot resolve in characteristic 0. That's basically, that would be, does this exist?
Yeah, they exist, yes.
Uh-huh.
Yeah, I can't really write them down for you right now, but they definitely exist.
Yeah, no, but okay.
Are those examples like of strange rings from Nagata, maybe?
Yeah, probably, yeah.
Yeah. So Nagata definitely has examples. Also, I guess we were talking about Crystal Rothaus earlier. She has a bunch of examples of non-excellent rings.
Okay,
this
I that she was very much into. So I actually learned at the time all these definitions, but now they have been forgotten.
Yeah.
Okay.
Can I ask one more question about the relationship to excellent?
Yeah, sure.
So I think of excellent as being, the definition, it's hard for it to stick in my head, but the definition of excellent that I read before is like something about the formal fiber being smooth plus universally catenary. So is this condition equivalent to that condition Or are they only equivalent in the presence of universally catenary? Do you see what I'm asking?
Yeah, so definitely the definition of quasi-excellent you're thinking of that doesn't have the universally catenary condition is equivalent to the one I wrote down as long as the ring contains the rational numbers. And this is a theorem, right, that the two definitions are equivalent. So yeah, and you don't need universally catenary in there. Yep.
Thank you.
Sure.
So this theorem essentially gives meaning to, or like, is the statement that says that you can only resolve singularities if the ring is quasi-excellent, right? Which is like this thing that you hear when people talk about this, right? Like they say, oh, your ring has to be quasi-excellent, something like this.
Yeah, that's right. So the reason why I cited EGA4 first is that they proved that if this property holds, like if you always have resolutions of singularities, that forces your original ring to be quasi-excellent. And so the conjecture they gave was that the converse holds. As long as you're quasi-excellent, you should have resolutions of singularities. And Temkin proved it in characteristic 0. Yeah.
Oh, I see. Okay. Now I'm understanding the significance of this. Like, it was only a conjecture then, I see. Yeah. But now it's been proved by Temkin. And that's sort of, I see, that's pretty cool.
Yeah. So that means I have.
Oh, I was going to ask, like, if something is not reduced, it's not going to be quasi-excellent, right?
No, you can have non-reduced quasi-excellent rings.
So you could resolve the singularity of something that's not reduced. That
Oh,
would
so
make sense.
I guess if you look on the right-hand side of my screen right now, the condition is that for every domain of that's module finite over that ring, it has a resolution. So the condition on resolutions of singularities is already saying that the ring T that you're resolving should be reduced.
Oh, I understand. Yeah. So, but I guess an answer to my question is like you can't resolve the singularities of a non-reduced ring. That doesn't make sense.
So I guess what I would say is that I don't really know what a good definition of a resolution of a non-reduced ring should be.
Yeah. Like, what should it be? Yeah. I understand. Yeah. Thanks.
Yeah, sure. Okay. So let me move on to the next section, which is about pseudo-rationality and Boutot's theorem. And so now you'll be able to see why I defined quasi-excellence first, which is that I'm only going to define pseudo-rationality in the case where I'm quasi-excellent and contain the rational numbers, in which case pseudo-rationality can be characterized in the following way. R is normal, and for every resolution of singularities, W to spec of R, the higher cohomology of W vanishes. So at this point, it's kind of hard to give a purely commutative algebra definition. So I apologize that I have to use schemes. It's not very clear the way I wrote it down that implies cohomology, but it does. And if you want to know why, you can ask me after the talk. And so if you're a geometer, this looks more like the definition of rational singularities, and they coincide in this context is what I'm saying here. Okay, so let me tell you the main ingredient in my proof of the main theorem, which is a version of what's called the Grauer-Riemann-Schneider vanishing theorem. And this is really the hard part, I think, of the proof, and I will not be proving it. So what is this statement? So let's consider a local ring R comma M, and let's say Noetherian local, just to be clear. And R contains the rational numbers. And let's consider a resolution of singularities of spec of R. What I prove is that in this case, this sort of scheme theoretic version of local cohomology vanishes for all I less than the dimension of R. Okay. So again, this is something that's, known before in some cases. So the first remark I'll say is that when R is again essentially a finite type over the complex numbers or really any characteristic zero field, this is due to Grauer and Riemann-Schneider and they proved this back in 1970, although this local cohomology formulation is due to Hartshorn and August. Right, so they did do it in terms of sheaves of differential forms. And I don't want to spend too much time talking about the proof. You can ask me later if you're more interested. So the proof reduces to vanishing theorems of the sort Grauer and Riemann-Schneider proved using two things. So the first thing I use is that local cohomology behaves well under direct limits of rings. And really you need a scheme theoretic version of this, so it's a bit more complicated. But if you imagine like local cohomology, you compute using a check complex, you take direct limits of the rings involved, those all fit as a direct limit of complexes, and cohomology commutes with complexes, like taking cohomology of complexes, direct limits of rings, etc. So that's something believable, I think. And the other thing I use is Zariski-Riemann spaces. So not only do I have to leave the world of rings, I also have to leave the world of schemes and work with these sort of valuation type spaces that, for example, GB is very familiar with, I think. But this is the main ingredient, and I'll use it to give you a sketch of the main theorem. Are there questions about this ingredient that I wrote down?
Sorry,
it is very interesting. Yeah, you're right. I'm kind of working on it, so it's very interesting that they come up. Yeah.
Yeah, I'm like excited now to hear this. Okay, we're listening now.
Yeah.
Okay.
Sorry, Takumi, do you really mean I less than dimension of R?
Oh yeah, I do mean I less than the dimension of R.
Okay, all right.
Yeah, so you might be thinking that it should be I greater than 0 or something like that. But the reason why it's switched is because there's a duality statement involved. So this is equivalent to the usual Grauer-Riemann-Schneider vanishing via a combination of local duality and Grothendieck duality, which switches the direction of which way the things go.
Got
Okay.
it. Yeah. Thanks.
Okay. And so, if I were giving this talk, right, I chose to focus on the invariant rings part of this talk. So I'm going to sketch the proof of the main theorem now using this main ingredient. So I just went back and copied the main theorem statement so you can see it on the right-hand side of the screen. And let's see how this main ingredient is used. So in particular, this proof is very different from Hans's proof, right? Because we use vanishing theorems instead of ultra products. So how do you prove this main theorem? Again, the statement is that if you have a pure inclusion of rings and S is pseudo-rational, then R is pseudo-rational. The first step is to do some reductions. So by Noetherian induction and localizing a few times, we may assume the following. First, R to S is a pure map of local domains, and spec of R minus M, so like the punctured spectrum, is pseudo-rational. Right. And so one thing I'll note is that we already know that R is Noetherian and normal by the two facts I proved earlier, right? That Noetherianity passes to pure subrings and also normality passes to pure subrings. And so the dimension 1 case is now done. right? Because a normal ring is regular in dimension 1. And so in dimension 1, there's nothing you have to show. So I'm going to consider when the dimension of R is greater. And so this is the first step where you really need to use quasi-excellence. The condition on spec of R is that for every resolution, something happens. And that's kind of an empty condition without resolution. So let's just take one of those resolutions and claim that it has the vanishing property we want. And to prove that, we're going to use the fact that S also has a resolution of singularities. And I'm going to call that map F prime. And so what I'm going to do is I'm going to descend the vanishing of cohomology condition from S down to R. And so how am I going to do that? Well, the hypothesis says that if I take the higher cohomology of W prime, this always vanishes. There is a map you get from WOW. And we want to show this map is injective, right? So if you're a sub-module of the 0 module, you have to be 0. And this will be what I prove for the rest of the talk. Okay, are there questions about that idea?
Can you just run down why we can assume that the punctured spectrum is pseudo-rational?
Yeah, so what the Noetherian induction says is that, basically what we want to show is that if you have a prime ideal P, and we know that all the localizations at points, let's see, at prime ideals that are strictly contained in P, those are all pseudo-rational. We want to conclude that P itself, when you localize there, you're also pseudo-rational. And so basically we kind of just like look at a chain of prime ideals and go step by step in the induction. Yeah, that's what's going on. But then you replace the original ring by the localization of that P. And by that inductive hypothesis, we know that all the other prime ideals, when we localize there, we already know it's pseudo-rational. So that's definitely something very helpful in the induction. Okay.
Thank you.
Yeah. So the rest of the proof is going to go in 2 steps. So the first one is a lot of notation. So there are 4 spaces I need to work with. I need to have a name for the punctured spectrum, the inverse image of the punctured spectrum inside of W, then the inverse image of U, the punctured spectrum, inside of spec of S, and also the inverse image of that inside of W. Prime. Okay. And so how do I prove this? Well, first I'm going to prove that we have a corresponding statements for V and B prime. I want to show this is adjunctive. So this is what step 1 is going to show. The way that I do that is, well, if I pass between V and U, we know that these are going to be isomorphisms since U is pseudo-rational. So it's a bit mysterious maybe if you don't know what pseudo-rationality should mean for schemes instead of rings. But basically, I've set it up so these 2 are isomorphisms automatically. And the way that you use purity is that these are isomorphic to local cohomology modules. Right? There's a long exact sequence connecting local cohomology and this sort of global sheaf cohomology. This map is injective. This is in Hochster and Roberts' original paper. If you have a pure ring map, it induces injective maps on local cohomology. And so this implies that this map is injective. And so this map is also injective. Okay, so let me write down the conclusion of this step. HI of VOV injects into HI V prime OV prime. And step 2 is where the main ingredient is used. You can fit the original map we were interested in into a commutative square. This map I know is injective by step 1. And to show that this map on the left is injective, it suffices to show this one is injective by the commutativity of the diagram. So what am I going to do? I'm going to look at the previous part in the long exact sequence connecting local cohomology and local cohomology, and sheaf cohomology. What fits here is this thing that we know vanishes by our main ingredient, by the Grauert-Riemann-Schneider type vanishing. So this works if the dimension is less than, or I is less than the dimension of R. If I is the dimension, you need a different argument, but it's still fine. And so by the exactness of this long exact sequence, this is injective. And again, by the commutativity, we know that the original map I wanted to be injective is also injective. So this is how you show that purity, that pseudo-rationality, at least in this case, passes to pure subrings. Okay, so that was kind of a very quick version of the proof, but hopefully it tells you kind of the ideas that go behind the proof is that purity gets used in this spot here, basically boils down to a statement about local cohomology. And the main ingredient shows up here in this long exact sequence where I want to make sure that this map is injective. And there's one more thing I want to mention, which is that I promised that this also proves Hans's theorem, and that's the case. So if R is a pure subring and R contains Q, and we know that every localization and then completed of S is pseudo-rational for all P prime, then R is also pseudo-rational. So the proof of this is you can localize and then complete to reduce to the previous theorem. So maybe in particular, I'll mention that this condition holds if R is regular. Or S is regular, sorry. And so we recover Hans's theorem as well. So that's all I wanted to say. So thank you very much for listening.
Thank you. Thank you. Very interesting.
Thank you. Any questions?
Thank you for making it in the language of commutative algebra as much as possible.
I tried, but you know, schemes do end up showing up. So
Yeah, well, of course, but you know, I really appreciated, you know, also the commutative algebra language as a background personally.
well, thank you for listening. Thank you
Yeah,
for
and
those
also
comments.
giving some of the proofs that always helps to actually see how things are done.
Mm.
Could I actually look back at the statement of the main ingredient, that vanishing stuff? I just wanna the hypothesis. Okay, yeah. Okay, and you said that like there's some duality coming in, right?
Yeah. So so maybe I'll just say that this is the statement I prove, and if you assume that R has a dualizing complex, then you can get a dual version of this as well.
Mm-hmm.
Yeah, that involves like the dualizing complex on W.
Mm-hmm. Okay.
Yeah, and then perhaps also, I mean, I know you didn't want to talk much about it, but if you scroll a little bit down, when you mentioned these risky Riemann spaces that you use there, that's yeah, I would be very interested to see the argument there.
Yeah, so maybe I'll just say briefly that the reason why they show up Maybe I'll add a page so I can actually just describe what's going on. So the reason why they show up is that if you have this map W to spec of R, you can definitely write R as a direct limit of a bunch of finite type Q algebras. Right? You just like kind of like keep adjoining things that are inside of R. And you can complete this diagram to have these W lambdas that are also have a limit that's equal to W, right? But the issue is that these things here are not regular. And so in Grauer-Riemann-Schneider's original theorem, for example, they proved that if you have a regular scheme mapping onto something else, then you can say something about vanishing. And so what I need to do is I need to take resolutions of these. Maybe I'll call them W lambda, and I need two indices. So mu lambda, or yeah, mu and lambda. And what I want to do is, okay, I know that the limit of these W lambdas is W. What is the limit of these things? And what I prove is that the limit of those is the Zariski-Riemann space. And so you end up saying that, okay, I'm interested in the cohomology for this map. The original statement, Grauer-Riemann-Schneider's theorem, tells you something about this map. So it tells you something about the composition from the Zariski-Riemann space back to spec of R. And then there's an argument to descend that back to W. But that's where it shows up.
Do you use the work of the Temkin for this or no? This is just...
So there's a lot of work of Temkin that I could be using, but I can... It is possible to write down the proof so that none of Temkin's work is used. And in fact, you can probably get away with, you know, the latest paper I would need is from '87, I think.
Okay.
Yeah.
Okay. All right. So that's how they come in. Okay. Interesting. Thank you very much.
Sure.
Very nice, and thanks also, you know, very nicely organized. I love this, you know, board that, you know, splitting.
Yeah. If you agree to that we put this on YouTube, this is gonna go viral. So well prepared.
I third all that. Like, this is so clearly laid out. It was beautiful. And the stop to ask questions, you know, it was just a very gorgeously exposited.
Yes.
Well, thank you for all the nice
highly
words.
appreciated. Yeah.
Can I ask you to go back to the slide with all the previous, like the little table with everybody's previous work on it that had?
I think it's on the right hand side.
I think they're both the same, right?
Oh, I see. This is the same side. Oh, okay. Get it.
Okay. This is the statement that if the inclusion is pure, these are all the statement for if the inclusion is pure, then, and the top is regular, then the bottom is both Cohen-Macaulay and quasi-rational, right?
Yeah, so the first row, the one that says one, is the Cohen-Macaulayness statement, and the second row is the pseudo-rationality statement.
Got it. Okay, so purity was already enough for that in Hochster and Roberts.
Yes.
I think of Hochster and Roberts as a statement about invariant rings, but all it is saying is it's a pure inclusion.
Right, so maybe I'll say that in characteristic P, like when P is positive, they prove that purity is enough to get regularity to induce Cohen-Macaulayness on the smaller ring. But they also use that to prove the equal characteristic zero statement about invariant subrings. So in that paper, they couldn't prove that you know, a pure subring of a regular ring is Cohen-Macaulay in characteristic zero, but they were still able to get the theorem about reductive groups in characteristic zero in that paper.
Got it. So then it's a characteristic independent statement about reductive groups.
Right. I mean, I guess you still need to contain a field, but yes. So they are able to prove something about reductive.
I see. So this answers the question at the very beginning I asked, is the ring inclusion not necessarily pure in when the group order is divisible by, like, for a finite for an invariant ring by a finite group, is the ring you know, because you gave the proof in the case that in the non-modular case. And I asked, okay, the proof doesn't work in the non-modular case, but does the statement still hold? And you said, I don't think so. So actually Hochster and Roberts, now that I see what Hochster and Roberts is doing, that means that, yeah, no, it totally, any example of a non-Cohen-Macaulay invariant ring gives you an example of a non-pure inclusion in positive characteristic by Hochster and Roberts.
Yep,
Right,
that's
exactly right. Yes. Yeah, yeah.
So great. So an example would be like the regular action of Z mod 4 on the 4 variable invariant ring on the 4 variable polynomial ring by cyclically permuting the variables in characteristic 2. That's a case where the invariant ring is not.
Oh, really?
Oh, I didn't know that example, but oh, thank you. You
No,
answered
no,
my
I don't know the
question.
examples.
Yeah, that's the smallest permutation group example. So it's like a thing I think about. So, but I didn't know that that meant that it wasn't pure, but now I know. Thank you.
Yeah, sure.
Any other question? There's no question. Let's thanks Takumi again. Thank you.
Thank you all for coming and
Very
for
nice.
listening to
Thank
my
you so
talk.
much.
So have a good spring break, everyone. So we'll see each other in 2